When we did moment of a force before, whether it's 2 or 3 dimensions, you can always use the cross product with the 3 by 3 determinant and get the answer. In 2 dimensions, you've got a shortcut here, if you want to think of it as a shortcut that may or may not help you. All right, so let's look at some examples here. Before we do that, any questions on what a force couple is and what the moment of a force couple is and why we call it a free vector, why we get the same result no matter what point we choose to take the moment about? All right, so let's try this example. It's not from the book, so you're going to have to deal with the drawing that I have here. Okay, so here you have like the faucet that might be on a bathtub. And if you see the dimensions, it's probably not really a faucet on a bathtub. You know, maybe if they were inches instead of feet, it would be the case. But you've got something that's shaped like that. And there's this pair of forces, both 150 pounds, and if you notice the reference triangles, they're on parallel lines of action. Opposite sense, they are a force couple. We're asked, what is the moment of the force couple? Now, because of what we just discussed and how we always get the same moment no matter what point we take the force couple about, they don't say find the moment of the force couple about point D or about point E or about point whatever, because you're always going to get the same result. So you're not going to see that full phrasing like we had before. What you're going to see is find the moment of the force couple, and if you want to, you could kind of put in here about any point, because you're going to get the same result no matter what point you choose, and you really don't even have to choose a point, because remember the result we came up with is independent of whatever point you're talking about. Okay? So we're going to get this result, and that result would be true for any point that we would want to take the moment about. And I'm going to show you that's true because we'll go ahead and verify it. All right, but anyways, let's just use the result that we came up with that says the moment of this force couple about any point is equal to the position of A with respect to B cross the force at A. Okay, since I've got the forces applied at A and B here, I can use that same notation. Like I said, if I want to put the position of B with respect to A, cross the force at B, I'll get the same result. Okay, I just need to draw a position vector from one point of application to the other, and then use the force that's at the end of that position vector. So if I write the position of A with respect to B, that means I'm looking at a position vector like this, the position of A with respect to B. So we'll work it out this way, then we'll flip it around and say, okay, what if we did the position of B with respect to A across the force of B, and verify that it's the same result. And then we'll also verify that we get the same result if we take the moment of these forces about any of the points in the figure. All right, so let's see. Position of A with respect to B cross the force at A. So we're going to need a 3 by 3 here. So I, J, K. Since it's 2 dimensions, if I wanted to play around a little bit with the F times D technique, I can, but I'll show you that a little bit later. Let's just stick with the general method, which is the 3 by 3. Now I need the position vector in the middle row. So I'm going from the point B to the point A. So if I just assign to this our standard positive x and positive y axis, when I move to the left by 3 feet, I'm going to say the position vector has an x component of -3. So I go to the left by 3, and then I have to go up by 1 in order to get to the point A. So the position of A with respect to B is -3i, going left by 3, positive 1j. And then it's 0k because everything's in the plane of the board here. The force that's applied at A, I need the x and the y components of that one. So the x component here, so this force that we see up here is going to have components that go to the left and that go down. So if I want the x component, the component that's going left, it's going to have a negative sign. And then I would say I want the cosine of the angle here, which would be adjacent over hypotenuse, so 4/5. So I have 150 times the cosine of that angle, which is 4/5. Okay, so if you want to multiply that and see what you get, I think it's 120, so negative 120. For y, the vertical component's going down, so it's also going to be minus. And the vertical component would be opposite of our angle, so the sine, 3/5. So negative 150 times 3/5. If you multiply that one, I think it's 90, so negative 90. And then again, 0 for k, because the force is in the plane of the board. So if we work this one out, let's see what happens. Now you cover up I, notice you get 0. Cover up J, you get 0. So you go to K. And here you actually have something. So we end up with -3 times negative 90 minus positive 1 times negative 120. That's in the K direction. 270 plus 120 makes 390. And if I check the units, I've got feet and I've got pounds for my unit. And I need my K direction, so I have a vector result. So the moment of this force couple, 390 foot-pounds or pound-foots in the K direction. So what does that mean? That means if we apply this force coupled to the rigid body, if we take any point in the rigid body and hold that point fixed, the axis of rotation that this force couple would create is going to be the z-axis, or something that's pointing in the direction of the z-axis, so straight out towards you. And then that 390 just represents something about the strength of the tendency that that force couple wants to impart rotation. Question?
In this particular case, it's attached to a wall, so it can't rotate, right?
It can't, but what we're saying is if the only point that were fixed were this point.
Oh.
So in other words, get the hacksaw out and cut it off from the wall and just hold this point fixed. Drive the tent peg through the point E so that the tent peg points right along the z-axis. That force couple will create rotation around that axis. Okay? Positive means it's going to be counterclockwise around that axis. If we were to sit out at the positive end of the axis and look, we would see counterclockwise, and you can visualize that just from the orientation of the two forces here. Okay? Now here's the thing, if we were to choose any other point, let's say we cut this from the wall and we just hold this corner fixed and apply those two forces. It's still going to generate the same exact kind of rotation around this point as it would about this point. Okay, and I'm going to show you that in a minute. But before I do that, let me just show you that this is true too. I said that you can take the position vector either way. You can do the position of A with respect to B or the position of B with respect to A. As long as you use the force that is at the end of your position vector. So if I want this to go from A to B, that's the position of B with respect to A, I'm going to have to cross it with the force at B. Okay, so let's first confirm that this gives us the same result, because you don't have to sit there and wonder, well, which way should I make my position vector go, and which force should I use in the cross product? Well, just make your position vector go whichever way you want, and just use the force that's at the end of it. So we're still going to have ijk here. Now the position vector that goes from B to A, we're going to the right by 3, so positive 3, and we're going down by 1. So to the right 3, down 1, it's going to be positive 3, negative 1, and 0. And the force is now the force at B, which is going to have components that are to the right and up. Now it's still going to be 150 times the cosine of the angle, so it's still going to be the negative 1, or the 120, but now positive 120. It's still going to be 150 times the sine of the angle, so still going to be 90, but now in the positive y direction here. So we're going to get the 120, the 90, and the 0 here. And when you go through the calculation, again, k is the only direction that's going to produce something. So what do we get? Positive 3 times positive 90. Well, that's essentially what negative 3 times negative 90 gave us. Minus negative 1 times positive 120. Well, that does the same thing as positive 1 times negative 120. Equals 270 plus 120 is 390k. So why does it work out that way? Well, it's arbitrary which point I call A and which point I call B. Okay? The figures showed this one is A and this one is B. But that was an arbitrary assignment. If I had called this one B and this one A, the force couple is still going to make the rigid body do the same thing. Okay? The way we label it, if I choose different letters, if I call this point P and this point Q, that doesn't change the way the force couple behaves. So just showing you that you don't have to concern yourself with the letters. Just draw a position vector that goes from one to the other and use the force that's at the end of the position vector that you drew. Okay? Now, I told you that we would get the same result about any point. Okay? This is the result. Let me show you that it is the result that we get about any point. So let's choose a couple of different points. Maybe we'll choose 3 or 4 different points on the rigid body and show that we still get the exact same moment vector when we take the moment of this force about that point plus the moment of this force about that point. Let's start off with, how about we take the point D? Okay, so let's take the moment about, we'll take the point D. Okay, so the point D. Now here I'm going to use my two-dimension FD shortcut, if you will. If I hold the point D fixed, let's focus on the force that's acting at A first. Notice the horizontal component has a line of action that goes through the point D. So that one creates no moment around the point D. Notice the vertical component is going to want to generate clockwise rotation. So I'm going to have a negative term here. The magnitude of the vertical component, if you remember, was 90, and the perpendicular distance from the line of action to the point D is 2 feet. So I get negative 90 times 2. Now I have to take the moment of the other force around the point D as well, because the force couple means, both forces have to be considered. So the horizontal component here, if I hold the point D fixed and I pull out this way, that's going to generate counterclockwise, so it's going to be a positive term. The horizontal components had a magnitude of 120, and now the perpendicular distance from the line of action to the point D, 1 foot. So it's going to be positive 120 times 1. And then the vertical component here, if I hold the point D fixed and push up on the point B, also going to generate counterclockwise rotation. So it's going to be another positive term. The magnitude of the vertical components for these force couples is 90. And yeah, we're going to need the entire horizontal distance now. So perpendicular line of action, or perpendicular distance from the line of action to the point D is the 3 plus the 2, so that's 5 feet. So you run the numbers here, and guess what you get? 390 pounds per foot, or pounds times foot. And because that's a positive, and this is a two-dimension, we know that's generating counterclockwise rotation around the k-axis, just like we see from here. Okay.
Yeah, that's true.
What? Yeah. Now notice, here's what's interesting too. You have negative 2 times 90 and positive 5 times 90. So if you combine these two, what you really have is 3 times 90. Right? If you factor the 90 out, you get minus 2 plus 5, which makes 3 times 90. Look at what was showing up over here, 3 times 90. And then you had a 1 times 120, 1 times 120. Okay? So let's try another point. Let's take the moment about E. You want to do E? Okay, that's the harder. Well, I was going to do A or B, but we can do E. And then we'll do either A or B after that, and I think by that time you'll realize that we're getting the same result every time. Okay, so if we go around the point E, let's start again with the force at A. Horizontal component has a line of action that goes through E. So no moment for that one. Vertical component, let's see, if I hold E fixed and I push down here, that's going to spin me counterclockwise, so I'm going to have a positive term. Vertical component has a magnitude of 90, and what's the horizontal?
3.
Perpendicular distance, yeah, 3. Does not surprise me that I get a 90 times 3 showing up here. And then let's see the force at B. Horizontal component, also generating counterclockwise rotation. So it's a plus. Horizontal component is 120. Perpendicular distance?
1.
1. Does that surprise you? 270 plus 120, 390 pounds per foot. Okay, I'll do one more and then I think we'll be convinced. Just take the moment around the point A. Now the two components that have lines of action through the point A don't generate any moments around the point A. Okay, see, if the force has a line of action that goes through the point, it's not going to create any rotation around that point. If this is my rigid body, and my point, let's say my point A is here, and I have a force that has a line of action that goes through that point, it won't generate any rotation. It might generate translation, okay? So if I can push here, it goes towards you. If I push here, it translates towards the door. It's only when I get some distance between the point and my force that I get rotation, okay? So that's why I can say, if we're taking the moments around A, this component won't create any moments around A. The line of action goes through A, but what about the two components here? Hold A fixed, horizontal component, counterclockwise, so positive 120. Perpendicular distance, 1. Vertical component, push up on the point B, counterclockwise, magnitude is 90. Perpendicular distance is 3. The same numbers keep showing up all the time. 390 pounds per foot. Okay, guess what? If we did this around the point B, 390 pounds per foot. So this is what I wanted to illustrate to you, that when you have a forced couple, if you were to take the moment of those forces around any point, you're always getting the same result. So you really don't even have to talk about taking the moment about point D or point E or point A. You just say, what's the moment of that forced couple? And whatever the result is, you know that would be true for any point that you need to consider. Okay, that's an important thing to keep in mind when we get to equivalent force couple systems that we may see today, but most definitely next week. Okay, not sure we'll get there today or not. All right, so any questions on this one and how we worked this moment out 5 different ways and we got the same result every time? Okay, now those last 3, just be aware that all we did is find the magnitude. If this were like a test or something and it said find the moment of the force couple, moments are vectors, so you would have to then express that in vector format. Magnitude 390, direction counterclockwise arrow. Okay. All right, so that's 2 dimensions. Let's try one in 3 dimensions.